we had was this. When the dust settles, we had the following for f of x, and that could be an n component vector. It's the function around some point. Instead of the first derivative, the chain rule gives us a whole collection of first derivatives evaluated at a point xi minus x0 I. So n variables. And then the second derivative, double sum I and j, squared f dxi dxj xi minus x0 I xj minus x0j. And then there are higher orders, and we even saw from my derivation, we would just have a triple sum, a quadruple sum. So this is very mechanical, but this is as far as we want to go for the purposes that we're pursuing. And always remember, n equals 1. This is the one we really should know. Up to here, this statement is just the definition of the derivative practically. Okay? And but then you start having higher derivatives, so you can identify these terms with each other, and you realize that your first derivative criterion for a critical point, which we learned down here in one variable, has to be that all of the first derivatives vanish at a critical point. And your second derivative criteria is more complicated. So at a critical point, if it's a local minimum, we want this to be positive, right? Now the second derivative is an entire matrix of second derivatives. And from linear algebra, we get certain properties in that matrix. In physics, fortunately, just by construction, we're going to know whether it's positive, definite, or not from the outset. So we have to just become accustomed to this, and this is a square matrix, so I could just call it aij e squared f dxi dxj. And because they're evaluated at a point, those are all constants. And we can see by construction, if it's a well-behaved function, it's symmetric. So this is called the Hessian matrix. You want to look something up? And I'll just put here if aij is positive definite, then x0 is a local minimum. And that's, of course, if these guys vanish, right? For estimated positive definite x local minimum, given that we're at a critical point. So I think we had that in the notes last time too. Right? So that's the point at which we are. And now we're going to go translate back into our Lagrangian problem for small oscillations. And do some examples with the small oscillation Lagrangians. Good. Yeah. You just have to get accustomed to these. It's mixed partials, so you just knock them out like a machine. Make sure you evaluate it at a point so that they're constants, and then you're good to go. Okay, so we're applying this to the with the small oscillation Lagrangian that I put up last time. Did I put much of it up at all? Small oscillation Lagrangian. What we got there? Yes. And did we do the equation of motion on that one yet? I don't think so. Good. So yeah, now we can put the small oscillation Lagrangian back up. I filled in all the gaps here on these definitions. So yeah, this has to be done a few times on repeat. So I'll just put here recall. We started with this very general form of Lagrangian Aij of Q, Qi dot Qj dot minus U of Q, Q1, Qn. And we've learned that that's a very general form. And that's, it's a big task to construct this thing. And then, so this is the first step. The second point is that U of Q has a local minimum at Q0. So then the third thing is to expand U of Q in a Taylor series equals U of Q0, which is just a constant. Then just using this nomenclature, Qi Q0, minus Q0i. So this sum here is the one that vanishes because we're at a critical point, right, with a local minimum. So this whole thing goes away. And then we're left with this second derivative matrix, E squared U, dQi, dQj, Q0, Qi minus Qi0, Qj minus Qj0. So this is where the important step is taken. So you've done that expansion just the way we've been discussing here. It's the local minimum of that function here. So basically, we're going to let Kij be these second derivatives. We're deliberately making them look like string constants. Deliberately. They are the second derivatives. It's a symmetric matrix, evaluated at points of the constants, and then we let x of I equal Qi minus Qi0. And I'm just going to write here equals small. It's the same thing we do all the time. Right? Very, very small. And also, we're going to do the same thing here. We're going to say Aij of Q0. We're going to define that as Mij. As over a mass, it doesn't have to be a mass. We're going to call it that. So this is also a matrix, and you can also do that if Qi minus Q0i is small. Small means small enough. So if you do that, you turn this Lagrangian into the small oscillations Lagrangian, because this, this xi dot is the same as the qi dot. And it's this construction that is so useful. It saves you so much work. Because if you want to take the equation of motion of this thing, it can be crazy. It can be really difficult. The equations of motion of the small oscillations Lagrangian are just beautiful and simple. So this is what we now have. 1/2 double sum ij mij xi dot xj dot minus 1/2 double sum ij kij xi xj. This is the object that we're going to work with. And then on all these systems here, we're going to set that up systematically. So the way I'm doing it this time around is I'm going through the theory first, and we're going to come back to all the systems one by one, okay? So there you have it. And you recognize these are quadratic forms. That's what this double sum with the matrix and these variables is called, quadratic form. So you have to definitely get used to these. They're all over the place in mechanics and physics. Yeah, so what do we do next when we have Lagrangian? Get the equations of motion. The thing is, by doing it this way, we get them once and for all. Okay, so I'm going to go through with the equation of motion. We're not going to have to do it again, but it's an important process. So what we're looking at is d over dt partial L partial x. And since I have I and j, I have to choose another letter, k dot minus partial L partial x k 0, and I'll even tag it with small oscillations here. Because that's our program. You have to take those derivatives. This is a one-time operation. But the job you guys are always going to have to do is start with, construct this thing and then go through these steps, right, to get these matrices. We'll just do this one right here, okay? Okay. This is a good exercise. We've done this related calculation, similar one a couple times already. Nothing wrong with that. So we're going to, in fact, it all comes down to calculating this. We do this calculation carefully, everything else falls in our lap. So we have d over dx k dot of this expression, 1/2 double sum ij xj dot xk dot. And we're going to have 1/2 double sum ij, and these are constants, so this is why we did that small oscillation Lagrangian, because we can differentiate all the way through here, and then with respect to xk dot, we just have these dotted quantities, so they're partials. So the first one is going to be delta kj, right, for this thing here in xk dot. And the product rule is going to give us xj dot, and then the partial. Oh, my bad. Back up here. not jk, ij. Let me get away with anything. What's more we feel? Okay. So we can differentiate through all of these. We've got the k, so we have delta ik or ki. That's this derivative of that one there, and then xj dot. Then we've got xi dot, and then delta, Kronecker delta kj. sum, we're going to set I equal to k. So we're going to have sum over j m k j x j dot. So the Kronecker delta, when you're summing over the sum over I, it's only when I equals k that you get anything. So you name that mi mk, carry j down j xj dot. And the second one, we're going to do something similar. It's only when j is equal to k that we get a non-zero. Okay. So when k is equal to j, or when j is equal to k, so we have mik xi dot. Deja vu, right? We've seen this before a couple times. And now we make use of the fact that this is symmetric, so we can have I m k I x I dot, and then we're summing over I here and j here. So both of these are labeled with a k. And both of the sums are the same; they're labeled with a k. So 1/2 is 1, 1/2 is 1. Then I have m k j x j dot j equals 1 to n. So this is great because we've really taken care of the only one we have to. This one here is going to have the same form because the K matrix here, these are xi, xj without a dot, but we're doing partials with respect to those. Here we did partials with respect to the dots. So we've actually done the entire calculation. It'd be here the same, the case of K is going to be a little awkward, but it's not that awkward. So we've now done the following. So we have the complete time derivative of this thing right here is just going to give us a double dot, right? Because again, and you see why it was so important to simplify those functions of Q. Okay? So what we now have is, from this, I'll write it right underneath here, we now have sum over m, so k, j, x, j, second derivative, minus, which is going to, minus a negative is going to give us a plus, sum over k, so k, j, x, j equals 1 to n, j equals 1 to n, equals 0. And look at this, k equals 1 to n. So it could be any number you choose. We got a couple of ways.
Not j here or no?
There's no dot here. Yeah, no dot here. Because these derivatives were just, with respect to these x's. Yeah, but this calculation I just did have the same form as this one. Right? So we just inherit this. Of course, we got to stare at this for a moment and make sense of it. But we will. It looks very complicated. But actually, what if n is equal to 1? Before we even move on, what do we have here if n is equal to 1? Let it all simplify in your mind here. Yeah, if n equals 1, we just have an m x second derivative plus k x equals 0. Simple harmonic oscillator. So what we have here is coupled oscillators. Right? Coupled oscillators. And the way to make sense of this is to pull the summation out in front. Okay, and it applies like this many extra dots are fatal. going to rewrite this thing like this. Sum over J. M A J X J second derivative A J equals 0. What you see here in your mind's eye is matrix multiplications. These are just like formulas for matrix times vector. So let's just call M the matrix M X second derivative plus AX equals 0 if M K are M by M matrices. You guys recognize that as row times column? Like this would be a row times a column for a K times X. This would be a row times a column for M X double dot. So I'll put here as a note, I want to recognize the matrix multiplication here. And if you do recognize that, then you've got a simpler type of logic, matrix times vector, matrix times vector. And then you have linear differential equations with constant coefficients. So also note linear multiplication, linear differential equation with constant coefficients. Constant coefficients. And under those circumstances, you justify it in saying, let's let X sub J be equal to A sub J e to the I omega t. That's a trial solution that will lead to success. The reason is that linear differential equations, constant coefficients have an exponential solution. That's generic. So if that's the case, then X sub J second derivative, bring down I omega 2 times. The I squared is minus, so it equals minus omega squared AJ to the I omega t. And then we can take this into our equation up top here. And what we get is sum over M I J. We're going to get a minus omega squared. We're going to have plus KIJ. Right, both of these have the common factor, so we've got the AJ e to the I omega t equals 0. So again, both times column. This one we can actually leave out. Okay, it's common to each one of these equations. So I'm just going to strike this one from the record. And again, we can now look at this as a matrix multiplication. We can go through now. Okay, so again, we have a matrix multiplication. So we can look at this as the following. Negative omega squared M plus A times vector A equals 0. That's what this one translates into. Because again, this was just, I didn't even have to write this one up here in the first place, okay? And, then again, row times column. And now this is one big matrix. Right? This is the matrix negative omega squared m plus k as a matrix. And now you're in linear algebra. The only time this kind of an equation has a non-trivial solution is when this matrix has linearly dependent rows and columns. So I'll write here from linear algebra. Non-trivial solutions. Comma. When. Would you remember the criterion for that? So this, remember, this thing is a matrix, the n by n matrix, when determinant of negative omega squared m plus k is equal to 0. And so we actually have to construct this thing, take its determinant, and its determinant is going to be an nth order polynomial, and its roots are going to give us the omegas. So what we've constructed here is the whole recipe for success. And remember, this M is our Mij matrix, same as the K is our Kij matrix. This thing is called the characteristic polynomial. So we construct the characteristic polynomial. Construct the characteristic polynomial, and then frequencies omega sub 1 to omega sub n. And because this is an eigenvalue eigenvector column, we can also get the eigenvectors corresponding to the so the frequencies omega 1 to omega n and the corresponding eigenvectors. A1 to A sub n. So we did these once and for all. We don't actually have to write these out whenever we solve these problems. We have to do the construction that gets us the n and k, and we have to do the characteristic polynomial, and then get the frequencies, and if we want, we can also get the eigenvectors. And they'll have this mean too. So what we're going to do is start with the two masses and three springs. Did I put that up in your notes? Two masses, three springs?
There was something we were talking about that.
Okay. 15 minutes, and we got time. So yeah, what we want to do is draw that thing, and I'm going to mention now it's related to this problem very closely to the two pendula in the spring. In fact, mathematically, we're going to see there's an equivalence there. But yeah, let's start with these two masses, three springs. And then hopefully we have enough material for you guys to get some practice. Friday we'll try to go through this whole thing. I think it should work out pretty well. We're in no hurry. We're ahead of the game, I'm pretty sure. Okay, so. That's right, well, this system, the derivatives, we'll see have been done for us. So the system that we're talking about is we have a spring, a mass that's all we had, that would be our harmonic oscillator, right? But what we're going to do is connect it to another mass with a different spring, and this second mass is going to have a third spring connected like that. Okay, so there's certain symmetry to this system here. Two springs on the outside, different one in the middle, and we can actually intuit so the equilibrium position x1 and x2 are both declared to be zero. If there's then all the springs are relaxed. So we can do a number of things with this system. Suppose we displace each mass to the right by an inch and let go at the same time. What's going to happen?
Basically have something similar to the harmonic oscillator, right?
Each one of these is a harmonic oscillator because this is a massless ideal spring. It's not doing anything, right? And so we would know what the frequency is. So omega 1, we're just going to say is root k over m. In fact, we're going to discover that that's one of the two frequencies the system has. The other thing we could do with this that's symmetric is we could pull both of them apart a centimeter or two and let go. And then what kind of motion would we have? I pull them apart symmetrically and let go. What are they going to do? They're going to go against each other like that, right? Because we did it symmetrically, that spring is effectively cut in half. And it has twice the spring constant. So what we'll find is omega 2 will be root k plus 2k prime over m. So we're actually going to discover that by going through the whole formalism. And these two types of motion are called normal modes. A random displacement of these things, you smack one of them, and they're both just going to be bobbling around, seemingly chaotically. But in fact, the motions, those random looking motions will actually be composed of those two ideal symmetric ones that we just talked about. We're going to prove all that mathematically. Okay? So what we have to do for starters is find the Lagrange. So this is just based on our deep physics intuition. But we're going to prove these things. So what's the actual Lagrangian of this thing? The Lagrangian, we've got for the first mass can move independent of the second one. I can just hold the second one down, the first one will move. And the kinetic energy for the second particle will be like that. That's the plus sign. Now I'm going to bracket out the entire potential energy. The potential energy is just the energy stored in the strings. So we have a 1/2 k x1 squared. The middle spring only stores energy if there's relative position change. Okay. Like I said, if they're moving in concert with each other, there's no energy stored there. So we get a 1/2 k prime x1 minus x2 squared. And for the third spring, it's a 1/2 k x2 squared. So that's our Lagrangian. We don't have to do derivatives per se on this one. We can use the formalism of the derivatives, but we want to put it into a standard form. And just to show you guys, this one here is M00M. Without further ado, would you agree with that? That's the matrix for the masses. This one is a little trickier to read off. But since this is, actually it's not a homework problem, is it? I'm going to prove this. I'm going to write it down. In fact, remember, this matrix is in front of it would be 1/2 for everything, remember the 1/2s? So there's an x1 squared here, and there's an x1 squared here. So we would have a k plus a k prime. And then there's an x2 squared here, and this will be a positive x2 squared here as well. So we would have a k plus k prime down there. What about the off diagonals?
Negative.
Negative 2k prime.
We've got a negative 2k prime here, right? But we're gonna split them. So we're gonna put one of them here and one here, so it'll be negative k prime. That's an example of making the matrix symmetric. Good. Yeah, so be sure you see what's going on there, because you can see we've already done all the work. We could have taken second derivatives and all, but this thing was built in second derivative springs. So yeah, we can actually cut to the chase and try to find the eigenvalues of this matrix. And I've got 5 minutes. We're going to do this. Okay, so I got to erase this here. I think next time we'll start with making sure we write down all these steps in order, what has to be done. So next, determinant of negative omega squared m plus k equals 0. And that means the determinant of negative omega squared m plus k prime. And then here I've got a 0. I've got negative k prime on the off diagonals. And then I have negative omega squared m plus k prime. So that determinant is equal to 0. And you can see these are the same, so I'm going to write negative omega squared m plus, put parentheses around here, squared minus, these cancel, k prime squared equals 0, right? So I can write equals k prime squared. This is a good trick, because I don't want to multiply this thing out. What I want to do is write it negative omega squared m plus k prime is equal to plus or minus k prime. That shortens the work considerably. So yeah, I did the determinant here, put this on the right side, took the square root of both sides, I get a plus minus for one of them. And now you can see we've got negative omega squared m plus, if I take the plus sign, I've got k prime on both sides, I cancel that away. K equals 0, and so my omega plus is just equal to root k over m. As advertised over on the board there. And if I take the minus sign, I have negative omega minus squared, m plus k prime equals negative k prime. Over to this side brings it over to 2, and I get my omega minus equals root k plus 2k prime over m. Anyway, so we nailed it. We got it done. This is a really important example. You guys should practice this one so you can just knock it out. Well, we're going to do a lot with this system. This one has all kinds of distributions. You know, we could take this as a proof of that property of cutting an ideal spring in half and doubling its spring constant. But there's other proofs of that theorem as well. Good, there you have it. So Friday, just get some practice on any and all of the things that were up here, and we'll go through them.